Okay, so in the interest of time, we're going to go ahead and get started. Good afternoon, everyone. My name is Diane Lechner. I'm the Vice President of Customer Experience for Midland Scientific. Thank you for joining us today for our webinar here with Erlab. I'm going to go ahead and kick things off, and then I'll hand it off to Tim Campbell, who'll be leading the presentation today. I see most of you guys are already all on mute, so we appreciate that. If there are questions, you can put those into the chat, or we will leave some time at the end for that as well. So introducing the speaker today, so Tim Campbell, he's the Director of Filtration Integration. He brings more than 25 years of experience in construction safety, hazardous waste management, and also laboratory filtration. He's been providing laboratory filtration safety solutions for Erlab since 2016. And he's currently the Director of Filtration Integration at Erlab, and he helps laboratories become safer and more sustainable through filtration. So very excited to have Tim here today, and I'll hand it over to you, Tim. Thanks.
Thank you, Diane, and I want to thank Midland Scientific for setting up this webinar, and I'm happy to talk to you today about how you can make your lab safer through filtration and how to mitigate often overlooked sources of chemical inhalation exposure. To give you a little background, Erlab is a laboratory filtration company. Hold on one sec. My slides are moving forward. Let me share again. But yeah, we're a laboratory filtration company. We actually invented the first ductless fume hood over 50 years ago, coming up on 60 years. And technical difficulties.
Joys of technology. You're all good.
Yes. All right, yeah, my slide did not move forward, did it? So.
It did not. It always works in the practice, right?
Yeah, exactly. It showed up, and now it's not working. Hold on one sec. I even restarted my computer right before to make sure it was working fine. And
you're all good.
all right, there we go.
Perfect. Good deal.
All right, hopefully go smoother after this. So yes, as I was saying, Erlab, we invented the first ductless fume hood over 50 years ago, coming up on 60 years. At the time, our founder was in France. He was making lab furniture. He actually made an acrylic shield that would slide along the bench top of the counter that the researchers were working on. So when they were mixing chemicals, it would protect them from any adverse reactions. But unfortunately, there's nothing to be done for the chemical vapors that were being released when they were working with those chemicals. Well, he was a World War II veteran, so he knew the importance of protecting yourself from chemical vapors, because in the war he wore carbon filtration gas masks for mustard gas. So he was able to come up with a much larger filter and fan box that would fit on an acrylic enclosure and then capture the fumes of the chemical vapors that the researchers were working with, thus inventing the first ever ductless fume hood back in 1968. Now, Erlab's whole goal in the laboratory is to protect the lab people working there from the chemical vapors they're using. So whatever you're doing in the lab, Erlab's goal is to reduce any exposure you have to the breathing in those chemicals. We've been continuously improving our filtration technology ever since. We've expanded beyond ductless fume hoods into what we call our ecosystem of filtration products. All these products are available through Midland Scientific. With us, everything starts with our capped air ductless fume hoods. Those are the ductless fume hoods, basically an improved version of that first ductless fume hood that was invented back in 1968. They ship completely knocked down, so they're very easy to get into existing labs, get through narrow doorways, and there's about a 2-week lead time to ship. So if you need a ductless fume hood, you can get one on site in about 3 weeks through Midland. And we also partner with Lab Conco, and that's what we call our green fume hood. They integrate our most advanced filtration technology onto their research-grade structure. It's called the Lab Conco Echo or Arrow. That's also available through Midland. And then we've taken that filtration technology from our ductless fume hoods and moved it on to where you store your chemicals. You have open bottles in a closed cabinet with no ventilation. The chemical vapors and odors can build up. So when you open those doors, you kind of hits you in the face. You breathe it in. It's not good for you, but it also leads to poor air quality in the lab space. And then our last product is our ceiling mounted halo filtration unit. So this adds equivalent filtered air changes to a space installed similar to a light, and you can add carbon filtration for chemical vapors and odors, or HEPA filtration for particulates to improve the overall indoor air quality in the space. Now I'm going to touch on indoor air quality. Well, indoor air quality, the EPA, it's one of their top 5 environmental dangers when the EPA is looking at environmental risks. That's because we spend 90% of our time indoors. So you're always indoors, so you're breathing that air that's inside. And unfortunately, sometimes the air inside can be 2 to 5 times more polluted than the outdoor air. And as an adult, you breathe 8 to 10 liters of air per minute. You have about 12 to 16 breaths per minute. So whatever the quality of that air is in that space, that's what's going into your lungs, and that can affect your health. And across the world, poor air quality leads to about 6 million premature deaths. And usually it's because of some type of cardiovascular disease or complications that people get from breathing poor air quality. Now think about that. That's just for a regular indoor space. Now think about a lab space where you're working every day. You're using chemicals. You're producing chemical vapors from everything you're using in the lab space. You may be producing particulate matter. You may be doing grinding. You may be using powder to do sample prep. You have equipment in there that is constantly using chemicals, and whether it could be vented outside or it may just be venting into the lab space, and you're depending on your air changes to remove those chemical vapors and odors. So over time, that can build up in it. Just like any other space, you have off-gassing of your equipment, your floors, your countertops, any of the furniture there. That can lead to poor air quality. Then also you have your HVAC and ventilation. Most lab spaces require 100% outside air. So what happens when you have a poor air quality day outside? You bring all that into your lab space, especially during wildfire season. You bring all that smoke into your lab space because you have 100% outside air. You can't recirculate it and filter it through the rest of the building. That's all coming in. You have a nice, weather front come through, get rid of all the wildfire smoke outside, but then you still have all that poor air quality inside. So as you know, as you work in a lab, you do have chemical inhalation risks. And when we talk about chemical inhalation risk, there's typically 2 different types. There's an acute inhalation risk and a chronic inhalation risk. Unfortunately, I think most of us has probably had an acute inhalation effect at some point in time or exposure. Typically, maybe whether we're working in the lab or you're at home, you're cleaning your bathroom, you're painting, you're cleaning the paintbrushes with mineral spirits, and all of a sudden you start feeling lightheaded, your eyes are watering, your nose starts running, you may be coughing, your throat's burning. That's an acute inhalation effect. Fortunately, if you can extract yourself from that situation, get some fresh air, those symptoms usually subside. Then you're very cautious of that moving forward, because if you don't get out of that situation, you could have a coma, you could pass out, you could even die. That's something I may touch on in a little bit. But with the acute inhalation effects, you're always aware of it moving forward. The one that people aren't always aware of, the chronic inhalation risks. And those are what you have with chronic inhalation effects are, you don't really notice it. You're working with the chemical, it's a low exposure over time. There's no immediate effect. You don't feel dizzy, your eyes don't water. You feel fine, but then you find out it's years later, you may have complications. You may have developed asthma-like symptoms. There's actually a Norwegian study that followed over 6,000 people over a 20-year period using cleaning products, whether they use them professionally for their job or whether they, clean their house a couple times a week. They found that on average, people who are using cleaning products every day had a lung function decline similar to smoking a pack of cigarettes a day, even if they didn't smoke. So it's one of those things, you don't notice it right at first. And that's where most of the time in a lab space, you're going to have the chronic inhalation risks or effects that you don't even realize because you're just exposed to low volumes of chemicals. So when you are exposed to chemicals, who sets the chemical exposure limits? Here in the United States, we have about 4 major organizations that do it. You have the permissible exposure limits from OSHA, and that's legally enforceable, and that's the time-weighted average over an 8-hour workday, what you can be exposed to. Then there's ACGIH, who sets TLVs or threshold limit values. There's the Association of Industrial Hygienists. You have the EPA, who does existing or new chemical exposure limits, which is under the Toxic Substances Control Act. And then you have NIOSH, who has their recommended exposure limits, or RELs, which is often a 10-hour time-weighted average, which often can be lower than OSHA PL. So when you look at all those different institutions, are they all the same? And unfortunately, they're not. So you have each institution typically has a different exposure level for different chemicals. Sometimes they're in agreement, sometimes they're not. Sometimes that just has to do with the last time they actually analyzed data on any of those chemicals. So my advice is you always look at all the institutions out there and try to base your exposure off the lowest level. I mean, in this chart here, you see acetone, first chemical on there. There's disagreement between the three institutions there. OSHA says you can be exposed to 1,000 parts per million over the course of a day. NIOSH is only 250 parts per million, and ACGAIH is 750 parts per million. Now, there's agreement, it looks like, on diethyl ether and methanol, but then you get to toluene, and OSHA is twice what you can be exposed to as NIOSH, and then ACGIH is 10 times lower than what OSHA says you can be exposed to at 20 parts per million. And over time, those exposure limits typically get lower, which brings me to dichloromethane, or otherwise known as methylene chloride. You often use it in the lab space because it's a great chemical for synthesis. It's very good at dissolving substances. That characteristic that makes it good at dissolving substances for sample prep also made it a very good paint stripper and bathtub refinisher. And since the 1980s, where they started keeping track, the EPA found that over 88 people died due to exposure of methylene chloride when they were using it as a paint stripper or bathtub refinisher. Typically, it's because they were in a small bathroom, unventilated space. The acute inhalation effects on them were they never got to the fresh air, wound up leading to death. So the EPA determined that dichloromethane presents an unreasonable risk of injury to health under the conditions based on acute and chronic non-cancer risk and chronic cancer risk. So they banned it in all consumer use and most industrial use. They do still allow it in laboratory use, but starting last summer in 2025, they said if you were going to use it, you had to keep the exposure below 2 parts per million as an 8-hour time-weighted average, which is 12 times lower than what OSHA's PEL is. But you'd also have to put a workplace chemical protection program into place to protect the workers when they are working with dichloromethane. Last summer, we had an influx of inquiries for our ductless fume hoods because people were using dichloromethane for open bench chemistry. So if you're doing any open bench chemistry, think of this. Whatever you're mixing, if it's a low level, it's a low volume of chemicals, they may not be giving you acute inhalation effects, but you may be getting chronic health effects from that. And over time, that builds up because when you're mixing those chemicals in front of you, those chemical vapors pass right through your breathing. So what are you supposed to do? I mean, like with the dichloromethane, when they were reaching out, they didn't have any options. They had been doing this procedure for years, preparing samples of dichloromethane and other solvents. They didn't have access to a fume hood. So when you think about trying to reduce a workplace hazard, NIOSH, the CDC, has a hierarchy of controls. And you see it's an inverted pyramid here with the most effective at the top, the least effective at the bottom. So elimination. So we'll put in the context of dichloromethane. Could these workers who are using dichloromethane just eliminate the process? So typically it was for sample prep. Well, could they just outsource that sample prep? Most of the time it was not. They could not. So now the next step down, which is effective, is substitution. Dichloromethane, you see a lot of people have started substituting ethyl acetate for it. Ethyl acetate is a much higher exposure level, a little less toxic. So they started doing that to, get around the workplace protection program. Problem is, you're still doing open bench chemistry. So the next step down is engineering controls. That's where Erlab comes in. And with an engineering control, you're going to isolate the worker from the hazard. Whether they're working with chemicals or it's an electrical hazard, you're going to put some guard in place or some type of equipment that's going to isolate that worker from the hazard. As you go down the pyramid, you look at the least effective step is PPE. In the past, I used to collect hazardous waste and I'd wear the carbon respirators. And one way you found out it was time to change a carbon respirator is you started tasting the chemicals. Well, once you start tasting the chemicals, that means you've been exposed to them for a while. So that's why PPE is always the lowest, because it's up to the person to use it correctly. So I'm going to now focus on the engineering controls and isolating the worker from the hazard. So when you are working with chemicals and you think of an engineering control to reduce exposure to the chemical, most of us think of a fume hood. And if you think of a fume hood, you're probably thinking of a traditional ducted fume hood. That's probably what you're used to using. It's a fume hood enclosure where the chemical vapors are pulled away from you. And then that fume hood is connected to ductwork and a fan that's going to take those chemical vapors and blow them outside. It makes it the outside world's problem. All those chemicals are used. The problem is if you're doing open bench chemistry, you probably don't have access to a ducted fume hood. You don't have one in your lab. Maybe it's not working. Maybe it's full of equipment. Maybe you have one down the hall that you have access to once a week. So it's just much easier to mix the chemicals or do your process on the open bench. That's where ductless fume hoods come in. They're very easy to install. You don't need any infrastructure upgrades. You just need some counter space and a plug, and you plug it in, and then you can wind up being protected by the carbon filtration on the fume hood. So what exactly is a ductless fume hood? For those of you who don't know, it's that same chemical fume hood that you're used to using, that traditional one. But instead of having that ductwork, they're using an advanced carbon filtration system to capture the chemical vapors and fumes that are generated within the enclosure, returns clean air in the lab. It's not part of the HVAC system, so it's very easy to add. You don't need the infrastructure. You don't need to rebalance the lab air. You just need a traditional power, standard power outlet to plug it in. What sets Erlab apart from other ductless fume hood manufacturers out there is we have universal carbon filtration. That means you can capture acids, bases, and solvents all with one filter. And the other part that sets us apart is the safety redundancy we have by allowing you to put backup filters on top of the fan box. So in that picture there, that's our Captair 483. That's our 4-foot equivalent hood. It's behind me here in the corner. It has 3 filtration columns. So if you look at the top of the picture, it looks like a double stuffed Oreo, as my colleague Julie likes to call it. And the white, the cream part, those are the fans. So that's what's driving the air away from the user into the filtration column. Below the fan, there's our main carbon filter or primary carbon filter. That's what's doing all the work, capturing all those chemical vapors and fumes that are generated within the enclosure. But then on top of the fan, there's a backup safety redundant filter. And that's in case there's any temporary breakthrough past that main carbon filter. You're still protected by having that backup filter on the hood. And then in those white fan boxes, that's where you have breakthrough detection sensors. A solvent sensor or an acid sensor to detect breakthrough of solvents or acids, and it's going to alert you. But also by having those backup filters on the fume hood on top of the fan box, when you get an alert that there's breakthrough occurring, you're still safe because you have those backup filters capturing anything that broke through. That picture, it's hard to see, but there are HEPA filters on the hood that goes on first. And that's what sets us apart. We have that flexible filtration column where you can add HEPA filters if you're using powdered or having any exothermic reactions. It's actually very common today. I'd say probably about 60% of our applications now have HEPA filters on the hood. And just to break it apart, give you a better visual of that flexible filtration column and how everything stacks. This is just a breakdown of the filters that go on the Lab Conco Echo, our green fume hood. And you can see how each part's individual is broken apart. You have the HEPA filter on the bottom, the primary carbon filter, the fan box with the detection sensors that's driving the air away, and then that backup filter. So it's all modular. If you're not using powders, you don't need the HEPA filter. If you're, say, in a clean room and engineer space where you need to keep the particle integrity count in the space, you can put a HEPA filter on the exhaust side of the carbon filter just to capture any minimal carbon dust that may be released. And what sets our carbon apart is the design of that filter shell and the carbon recipe. This is what allows us to have a universal filtration in one filter. So we don't treat the carbon, we just have a special recipe. We bake to a certain degree. We use certain grain size. And what that does, it allows to have more surface area on the carbon. Having more surface area on the carbon allows for more absorption of the chemicals. Think of popcorn. Before you pop it, you have those smooth kernels with not a lot of surface area. Once you heat it or activate it like we do with the carbon, that kernel pops open and you have all those nooks and crannies inside, and that gives more retention space or retention capacity to the carbon. And what we do is we absorb the carbon at the molecular level. Also, our filter design is very important to have a nice even distribution of carbon through the filter, so there's no leaks, no preferential pathways, because air will find the path of least resistance. So you want nice even airflow through the filter. So to show you just the basis of how molecular filtration works, or the principle of absorption. So you have your activated carbon. So that's in the carbon filter on top of the hood. The hood's running. You're creating polluted air in there. You're creating chemical vapors. So the blue is the just lab air being pulled in the hood. The red, those are those chemical vapors you're creating. The air from the fan, the flow pulls those that polluted air away from the end user and up into the filtration column. And this is where the chemical vapors then adsorb to the carbon. They adhere to the surface of the activated carbon. And that's why having the more surface area allows for more retention capacity. And then as the air goes through, on the exhaust side of the carbon filter is that clean air. So you're pulling air in from the lab away from the user. Those chemical vapors go up with it. They go through the carbon filter. Clean air is returned to the lab. Now, how do we know it works? Well, as I said, we invented the first ductless fume hood over 50 years ago. So we have almost 60 years of testing data. This is actually a picture of our R&D center in France. And in this picture, you see we have all the ductless fume hoods there. There's no ductwork. We use them for our own research. But there is a glass testing chamber. And in this chamber, this is where we test the design of our carbon filter shell and our carbon recipe. And we've tested over 600 chemicals with each of our carbon filters. Those 600 chemicals represents thousands of chemical families and are 98% of the most commonly used chemicals in labs today. So what we do is when we're testing a chemical is we'll set up a filtration column. There's a ductless fume hood in that glass bubble or the test bubble. There'll be a main and backup filter on the ductless fume hood. Inside the hood, there is a hot plate with a dish. We then have a peristaltic pump using the chemical or pumping the chemical we're testing that day onto the hot plate, which is, as I said, inside that ductless fume hood. So it evaporates. That chamber is then sealed and the air inside is constantly sampled by a GCMS. And this test can take from a couple hours to a couple days, depending on the chemical we're testing and the exposure level of that chemical. And we'll continue the test until we detect 1% of the threshold limit value of the chemical we're testing in the airstream past the carbon filters. What that does is that allows us to have what we call a chemical listing. We adhere to the AFNOR NFX 15211 filtration standard. This is a filtration standard that was designed back in 2009, and it's the strictest filtration standard in the world. But this chemical listing gives us the ability to then test or analyze what you're going to use in the hood before that. So this chemical listing shows the retention capacity in grams. You can see ethyl acetate is on there. That's a good substitute for dichloromethane. It's about a 2,200 gram retention capacity. It's almost 2,000 more than dichloromethane itself. But as I said, we do all that testing. We have this database of chemicals. We have the chemical listing. And what we do before you purchase the hood is we have you fill out what we call a chemical questionnaire, a Valley Quest or LPQ lifetime payback questionnaire. And what this does is this allows our lab to analyze all the chemicals you're going to use in that fume hood to determine the filter lifetime. So we're going to want to know the chemical you're using, what type of container it's in, because the opening of that container, the size of that opening, whether it's a wide open beaker versus an Erlenmeyer flask, is going to create or produce a different evaporation rate. We want to know the concentration using the chemical at, whether it's heater or not, because that's going to increase the evaporation, how long it's used in there. From all that testing we've done, we plug all this into an algorithm. We're able to give you a filter lifetime in months. So we have a couple different ways you can fill it out now. The first is with this Excel spreadsheet. Now we have our new online eValleyQuest or safety program where you can log in and follow along and kind of fill it out based off the different applications you're doing, the different chemicals, a little more intuitive. And that's one of those things that's continuing to advance. So we're trying to make it easier for you to give us an understanding of the chemicals you're using in the hood. And we do all that so then, like I said, you can get a chemical or a filter lifetime in months. And during that stated filter lifetime, we're going to guarantee that no more than 1% of the threshold limit value of all those chemicals you're using in that hood would be detected past the exhaust of the carbon filters. So this is an example for our green fume hood. So an M4, that's 4 modules of filtration, that'd be a 6-foot hood. This example from that chemical questionnaire I showed you before, be a 48-month filter lifetime. So if you use the hood how you said it would, we guarantee during those 48 months, no more than 1% of the threshold limit value would be detected past those backup filters. And then we're also able to tell what breakthrough sensors would work. In this case, it'd be solvent sensor and the acid sensor because of the use of nitric acid, hydrochloric acid, the solvents as well. And then if you're looking at it and you're like, well, I don't know if I want to fill out that questionnaire yet. The first thing you can do is we have a short list of chemicals that won't either be captured by carbon filtration or aren't recommended. So it's anything that's not retained well. It's gaseous at standard temperature and pressure. So your noble gases, carbon dioxide, carbon monoxide, the NOxes, the SOxes, all those things. They're very light. They're just part of the air. They flow right through. And then applications that aren't recommended. They typically would need a specialty ducted fume hood. So for chloric acid, you need a washdown hood. A radioisotopes, you need a specialty line hood. Anything that's highly exothermic, open flames, you're going to want a canopy hood to dissipate the heat. Now there's chemicals we can retain, such as mercury, but we don't recommend using in our hood because it's extremely toxic, has a very low threshold limit value, and it's difficult to detect breakthrough. That's the same with anything that's immediately lethal, like hydrogen cyanide. We know we can retain it. We've actually tested it, but we don't recommend its use in the hood. So this is always a good starting point. Make sure you don't have anything on there, and then you can start with the chemical questionnaire. And we're always here to help you through your Midland Scientific rep on how to complete that questionnaire. I'm going to go on to some other sources of chemical exposure you may find in the lab. So this is a nice AI generated image showing open bench chemistry, chemicals stored on the wall, chemicals stored in a flammable cabinet, and a nice floating HPLC. And HPLCs are some of the lab equipment that we see produce a lot of vapors in the lab. So if you're doing HPLC, a lot of times you're making mobile phase on the open bench. So there's a two for there. You could be doing open bench chemistry with the HPLC, and then also you have the bottles and the tubing. A lot of times those tops crack on there. I've seen paraffin, foil, trying to keep the vapors in there. So instead of doing that, you can enclose a whole HPLC unit in a ductless fume hood. Same thing goes for rotovapes. Rotovapes you typically see on an open bench. It's a sealed system, but you gotta fill the rotobap, the solvents, before when you're out on the open bench. And then also they are a sealed system, but it's not completely sealed. They produce chemical vapors or odors within the lab space, reducing air quality, and any other equipment such as microwave digestion, where you're using acids to dissolve different samples. It's going to be heated. Sometimes those are just on the bench. They're releasing into the space. Same with the ICP-MS. That typically releases nitric acid. You may see in your lab space, if you have an ICP-MS, you may see some of the metal grates are corroding. That means you have corrosive fumes in the lab space. So that's something you want to think of. You have all different equipment in your lab. Look around it. Is it releasing vapors? Is it vented properly outside? If not, is it just releasing chemical vapors into your lab space? Well, if it is, there's a good chance we can enclose it in our ductless fume hood. So think of it as ductless fume hoods can also be ductless equipment enclosures. So this picture here, this is Butler University. This is one of their general chemistry teaching labs. They have 12 of our green fume hoods on the outside that the students use during class. They had 4 rotovapes on the end of each bench that they would use throughout the year. They found the rotovapes were contributing to poor air quality in the space, a lot of chemical vapors and odors. So what they did was they wound up enclosing them in our capped air ductless fume hoods. That helped significantly improve the air quality within the space. So think about it. If you have equipment, you can isolate it. So you can put it in the enclosure, which isolates the worker from the hazard, which is always the best step. If you can reduce any of the chemical vapors from being released in the lab space, be contained in a fume hood, and then the chemical vapors or particulates being generated within the enclosure, captured by the filtration. We have floor-mounted models available through LabConco. We also have a partner who can custom make just about any size hood you want to match any type of equipment you may use. And then the most common piece of equipment we see or recommend being put in our ductless fume hoods are balances. So think of our ductless fume hood as a ductless balanced enclosure. If you look around your lab, you may see a balance on the open bench. Or a lot of times you see a balance on the open bench and they have access to a ducted fume hood, but it's too turbulent in the ducted fume hood. They can't get accurate weighing results. So they just have it on the open bench. Typically, we hear from people after the fact, after they've had an exposure incident. Maybe they were weighing a hazardous powder and the researcher was exposed, or you're weighing liquid chemicals as well. Those chemical vapors are going past your breathing zone. Putting a balance in a ductless fume hood, which is very low turbulence, completely encloses the procedure, isolates the worker from the hazard, and will significantly improve the safety of weighing. Ductless fume hoods are very low turbulence, so you can actually weigh out to 6 decimal places. By having that flexible filtration column, you can have both HEPA and carbon filtration, so you can weigh both powders and liquids in the enclosure. Now, another very common application we're seeing in a lot of labs today, not even just the lab, just about anywhere, is 3D printing. 3D printing is very common, and what happens is when you heat the filaments that are used in 3D printing, you release VOCs and you release microscopic particles. The heating of that, the printing process releases that into the airspace. So you can enclose the 3D printer in a ductless fume hood. Again, you'll have both the HEPA and carbon filtration in there. You're going to isolate the workers from the hazards, and you're going to significantly improve the safety of the 3D printing. Now, sometimes I've had instances where it's a 3D printing lab and there are just too many 3D printers to enclose the ductless fume hoods. It just doesn't make sense. And that is where our halo filtration unit comes in. So this is a ceiling mounted unit. It installs similar to a light, so it's going to be hung by threaded rod and electrically wired in, but it's going to add filtered equivalent air changes to the space. So for 3D printing, typically what I've done is it's a 3D printing lab. We've sold both a carbon version for the chemical vapors that are produced from the heated filaments from the VOCs being released, as well as the HEPA filtered version to capture all those microscopic particles. Again, it's not as good as a ductless fume hood that is going to isolate the work from the hazard. But in most of these instances, they've been able to set the printers up how they want them. They have the halos on, they're on running 24/7, and then they leave the space while the printing is going on. So by the time they come back in, any of the chemical vapors or microscopic particles that were released are removed by the halo. The halo is going to increase the ventilation and the effectiveness of the space. It's going to improve basically your HVAC system because it's going to improve the mixing of air. The carbon filtered version is going to add 2 air changes for every 4,000 cubic feet of space. So think a 400 square foot lab with 10-foot ceilings, you need 1 unit. 800 square foot lab, you need 2 units. The HEPA filtered version, there's less resistance to a HEPA filter. So we're pulling a little more CFM. So you're going to want one for about every 525 square foot lab with 10-foot ceilings. Now the halo isn't just for lab spaces. That's where it started. That's where we saw most of them. But throughout your building, you may have air quality issues. You may have air quality issues in the kitchen, in the offices outside the lab. Maybe there's re-entrainment happening in your lab space. So some of the chemical vapors from one space are being transported to another. A halo is a cost-effective way to improve the air quality in all types of spaces in your facility. So it's going to help remove constant odors, bad air, as well as reduce overall particulates. If you're in an area with a lot of wildfire smoke, the halo can help reduce that as it's brought in through your HVAC system into your building. Because once it gets in your building, it's much harder to get that poor air quality out. Now on to chemical storage. So if you're using chemicals in the lab, you're storing chemicals in the lab. As I mentioned earlier, storage cabinets without any airflow, the concentration of chemical vapors can build up. Once a bottle's opened, it's typically leaching a little of those chemicals out all the time. And if you are, say, storing satellite hazardous waste containers in there, those are very messy. There's always chemical residue on the side. Sometimes the carboys, the tops are cracked, so you're releasing chemical vapors into there. When you open those cabinets, you're hit with that chemical vapors. It's pulled right into you. As you open the cabinets, the process of opening those doors pulls that chemical vapors right out into your breathing zone, right into your face. It's not good for you. It also contributes to poor air quality throughout the lab space, or even if it's not a lab space in a chemical storage room. So we have a unit called the ChemTrap filtration unit. This is going to integrate onto those flammable safety cabinets you all have in your facilities, or if you have any of the blue acid cabinets, we'll do the same thing. And basically, it's just a box with a fan, our carbon filter, and then metal tubing. Most of those flammable safety cabinets all have a 2-inch threaded port. You just unscrew the bung, you put the tubing in, plug it in with the filter in there, and you're good to go. You can do carbon filter for the chemical vapors. If you were storing any hazardous powders, you can do a HEPA filter as well. It's going to improve the safety and storage of both chemicals and hazardous waste. They're also very energy efficient, only pulling 20 watts. They run 24/7, pulling only about 35 CFM through the cabinet, constantly filter any of the vapors that come off. I mean, you may have a dozen flammable safety cabinets in your lab space. If there's new bottles in there, you probably don't need one for it. But if they're active bottles, you're storing satellite hazardous waste containers, you're going to want to try a ChemTrap on those to improve the safety for you as well as the air quality of the lab space. And then we also have our own standalone capped air and filter storage cabinets. On the left there in the picture, the large one, That is great if you're a QC lab and you have a lot of samples. A lot of times they're odorous. You have different samples. Where are you storing them? Probably on the counter in a closed cabinet with no ventilation. This adds carbon filtration to the cabinet. So all air is constantly pulled past all those samples, all those bottles. Chemical vapors are captured in the carbon filtration. Clean air is returned to the lab space. Same thing if you're storing any hazardous powders, you can add HEPA filtration to that. And we also have a smaller under bench storage cabinet. So if you're, your at-use chemicals, the chemicals you're using in the ductless fume hood, you want to store in there. Or if you have very odorous chemicals, or cathinoethanols, ammonias, those are the type of chemicals you want to make sure you're always storing in a filter cabinet. Now on to engineered spaces. So in engineered spaces, I see a lot of open bench chemistry. So when I talk about engineered spaces, so they've been talking about clean rooms and dry rooms. So think about a clean room. A clean room, the goal is to have no particulates in there, very low level of particulates, maybe semiconductors, different types of applications where you can't have a high particle count. So you have about 20 to 30 air changes coming in through HEPA filtration into the labs, into the clean room. It's typically going to be positive pressure because you don't want any particles getting in there. So if you have to use chemicals, you're probably using them on the open bench. You're not putting a ducted hood in there because that's going to go against the airflow of all that clean air. Well, with our ductless fume hoods, you can put our HEPA filter on the exhaust side of the carbon filtration, helps you keep that particle integrity count of the clean room, but then allows you to safely use the chemicals you're using, whether it's a spit coating application or say it's a medical device and you're using solvents. So that's where you got to think, oh, I can improve the safety in the clean room with a ductless fume hood. The other large application we're finding is dry rooms for battery manufacturing. Dry rooms, they have typically 0% humidity, 5% humidity. Same concept as the clean room. You have all this dry conditioned air going into the space. So if you need to use chemicals, probably doing it on the open bench because you're not going to put a ducted fume hood in there. That's going to then take all that dry conditioned air and blow it outside. There'll be more of that to make up. So especially in battery manufacturing, there's HEPA filtration for the powders as well as the carbon filtration for the liquid chemicals. So it's been a very big application. It's something where if you work in battery manufacturing, you don't have a hood, ductless fume hood is an option for you. As I said, very expensive to condition that air to make it either super clean or super dry. Which then leads me to comparing the operational carbon footprint of a ducted fume hood versus a ductless fume hood. If you look at the 20-year operational carbon footprint, there's a 94% reduction with the ductless fume hood. Tip of that all has to do with the makeup air. The gas and electricity need to heat and cool the air that is being exhausted through the ducted fume hood. And where you see the most energy savings, they're going to be in a high density fume hood lab. So if you work in a lab with multiple fume hoods, there's a chance that the space is overventilated. I mean, most of the labs we deal with are typically about 6 air change per hour when they're occupied. And depending on the size of your lab space and the number of ducted fume hoods in there, you may be well over that air change rate when all those hoods are in use. So in this example, I'm just going to use a 5-hood lab that's 40 by 40, about 16,000 cubic feet of space. If your air change rate is going to be prescribed by a hazard risk analysis. And like I said, typically it's about 6 air changes per hour. So in this example, if all 5 hoods are being used at once, they're 6-foot hoods with the sash open, they're VAV hoods. So with the sash closed, they're 150 CFM. When the sash is open, they're 750 CFM. You're going to have to design that lab space or your HVAC system to be able to have 14 air changes per hour when all those hoods are in use. So think about that. In the summer now, you have that hot and humid outside, so you have that dry air conditioned air in there. That's all being blown outside of the lab. Those 6 air changes would be enough to keep you comfortable. But now with those 14 air changes, that 8 extra air changes when all those hoods are in use, you're taking all that expensive dry conditioned air and blowing it outside, and you got to bring in more of it. That's why it's very expensive when you overventilate the lab space. Now we take that same example and we go with 4 ductless fume hoods and 1 ducted fume hood. Now 1 ducted fume hood, you're only going to use 750 CFM, which is well below the 6 air changes per hour that you need. So overall, you'd have about a savings of $6,000 per year based on 35% use throughout the week or throughout the year. And that's because the ductless fume hoods, they're not part of the HVAC system. They are not exhausting any of that air outside. They're independent systems that are basically recirculating air within the space. The chemical vapors are pulled away from the user, pulled up in the filtration column, and clean air is returned back into the lab with that lab space. So you don't need extra air. You don't need to over ventilate it. You can keep your air change rate at the what the hazard risk analysis prescribes. And now if you're designing a lab from the beginning, this is just an example. This is, say, a traditional lab space that was all ducted. You know, about 5 different labs there, a couple with a single hood, couple with 2 hoods, and one with 4 hoods. So if you look through there, you see the size of the ductwork, which is the red and the blue. On that ceiling, on the top, on the roof, you see the air handling units, the exhaust fans, and the cooling tower. In the basement, you see the size of the chiller, the cooler, and the boiler. Sorry. Yeah. Now, think about it. Now, instead of designing with 100% ducted fume hoods, let's go 50-50. Do 50% ducted fume hoods, 50% ductless fume hoods. You're going to see there's going to be a significant reduction in the total exhaust air that's needed. That's also going to allow you to reduce your air handling unit, your air exhaust fans, your cooling tower, the size of your chiller and your boiler. It's going to significantly reduce the upfront cost because all that mechanical equipment is going to be reduced. But then moving forward, it's going to reduce your maintenance because you're going to be maintaining smaller equipment. And not to mention, you're going to be able to stay at that prescribed air change rate. You're not going to overventilate the space. So you're going to have significant energy savings if you design the lab up front as a combination of ducted and ductless. So on a project where it was 77 ductless fume hoods and throughout 6 different teaching labs, they were able to reduce the size of their chiller by 260 tons. I mean, that was hundreds of thousands of dollars we saved up front, as well as moving forward for the maintenance of that chiller. It's much less expensive. So some of my concluding thoughts are Erlab's whole goal has been to reduce the chemical inhalation risks that laboratory workers face every day. So look around your lab, see spots where you could be exposed to chemicals, and think of ways that you could reduce that exposure. So you have open bench chemistry, think about a ductless fume hood. You have chemical storage, you have hazardous waste, satellite hazardous waste containers in your flam cabinet. You're having chemical vapors build up every time you open them. Typically, you know if there's one cabinet you hate going in because it smells, think of ventilating that cabinet, adding a chem trap unit to it. Or if you just want to improve the overall air quality in space, the ceiling mounted halo filtration units. So they don't just have to go in a lab, they can go in your office space, conference room, lunchroom, just anywhere where you want to improve your air quality in the space and improve the air that you breathe. So Erlab provides energy efficient solutions to filter the air, clean it for you without infrastructure upgrades. It's all available through Midland Scientific. We're always happy in this room I am in. This is what we call our Inspiration Center. We have all the equipment set up. So if you'd like to, after this webinar, reach out to your Midland Scientific rep and get us involved. We're happy to have a Teams or Zoom meeting with you to go over how the products work and talk about your specific application or your specific concerns. I'm going to stop sharing the screen and then open it up to any questions you may have.
Great, thank you, Tim. That was a lot of great information. I do have a couple questions here. If anybody else has any questions, go ahead and put them in the chat. So the first one I have is, would the Halo unit work in a chemical stock room to reduce odors, and how many would we need?
Yes, they would. Actually, that's the first place I ever sold halos was in a chemical stock room in a hospital. They had a chemical library of these shelves that would go back and forth. There was like an old library where you wheel them and it smelled because the bottles weren't open, but they were leaching fumes, whether they're powders or liquid chemicals. So in that space, it was big enough that we installed 2 halos, carbon versions in there. So it's going to depend on the size of your room, but we recommend adding about 2 air changes per hour, or the equivalent of 2 filtered air changes per hour in the space. So if you let us know the size of the space, we can size it for you. But think of 1 halo for every 400 square feet. The 400 square foot lab, 10-foot ceilings, you're going to add about 2 air changes, so it's about 4,000 cubic feet of space. If it's twice that size, you're going to need 2 units.
Awesome. And how often do you need to change the carbon filters?
That's going to depend on what you're doing. With the Halo, it's typically 18 to 24 months. The chemical storage, it's typically a year. Every year you want to change the filter. And then on the fume hoods, it's going to depend on the volume of chemicals you're using. So that chemical analysis that you fill out, that chemical questionnaire you fill out, and the chemical analysis our lab provides, they'll be able to tell you how many, in how many months you're going to have to change the filters or how often. Typically, it ranges from an ideal situation, 1 to 4 years, depending on the size of your hood. As you get larger hoods, you have more filtration columns. You can sometimes get longer filter lifetime, depending on the application. But that's also a good part of filling out that chemical questionnaire beforehand, because then it knows that you'll be protected, but it also gives you your basic cost of operation moving forward. How often you're going to have to change your filters, and you can plan that out or budget for it.
Looks like we got a question in the chat. How do I dispose of the filter?
So the filters are deemed regulated non-hazardous waste. So if you have an on-site hazardous waste collection company, typically they can dispose of it for you. If not, you can basically, when you order the new filter from us, it gets shipped by a UPS in a box in a bag. Basically, you can take that filter, put it back in that bag in the box, and ship it back to us. Obviously, we need a PO for it, but you can ship it through UPS. We recommend high temp incineration. We recommend high temp incineration because typically the high temp incinerators are very regulated. So basically, everything that's captured on that filter in the carbon that gets absorbed, once it gets heated in a fire, it gets released, but it gets captured in those high temp incinerators. They have scrubbers that are basically capturing everything, or 99.99%. I think it's EPA, the regulation 267, that those high temp incinerators have to destroy 99.99% of all the constituents of what they're incinerating. So, and then basically that filter turns about half a cup of ash, gets put into a landfill, and for about each filter that is high temp incineration, you get about 73 kilowatt hours put back onto the energy grid, because typically high temp incinerators will put energy on the grid.
Great. If there are no other questions, we have recorded the webinar today, so we'll send that out along with a copy of the slides. So if anybody missed the webinar today, they'll get a copy of everything. And then if you want to review the slides, you can go back to there as well. So thanks everybody for your time today. We really appreciate it.
Thank you.